we can actually see this. We'll stick some numbers in here in just a second, but let me actually demonstrate how this can be very important. I've got another demo here. So I've got, I can actually pick this up, I think, so it'll be all right. I've got what's called a bimetallic strip here. This is a strip of metal that is copper on one side and steel on the other. Now, if copper and steel have different coefficients of expansion, we would expect the two sides of this strip to expand different amounts when heated. Well, we can actually demonstrate that. Again, I'll turn this, light this thing. There we go. And I will heat up the strip, and let's notice what happens. We notice that it starts to bend. Now, why is that? Well, it seems as though as it bends over, the side on the outside of the curve, the metal on the outside of the curve, is longer than the metal on the inside of the curve. So that would seem to indicate that the copper is expanding more than the steel is. In other words, the copper must have a larger coefficient of expansion than the steel does. And if we cool it back down, we notice that it straightens right back out. Okay, let's figure out what the units are for alpha. We have that alpha is equal to delta L over L naught delta T. So the units of alpha will be the units of delta L, which is a length, so meters, divided by the units of the initial length, which is a length, obviously, so meters, times the change in temperature. Now, typically we'll be using centigrade, so divided by degrees centigrade. Well, the units of length cancel, and we end up with the units of alpha, the coefficient of linear expansion, being inverse degrees centigrade. Okay, so let's stick some numbers in here, and let's see what we get. Let's imagine we have maybe a long steel railroad track. So here's a railroad track that's a long piece of steel. Let's say it's maybe 1 kilometer long. So 1,000 meters long. And let's look at this, what happens to this from a cold day in winter to a hot day in summer. So let's imagine we have a temperature change from, let's say, 0 degrees Celsius, which would be a freezing day, to something like maybe 100 degrees Fahrenheit, which would be about 38 degrees centigrade. So let's say we've got a temperature change from 0 to 38 degrees centigrade. Well, just ask yourself, how much do you think this railroad track will expand? Maybe just a little bit, something, a few millimeters, a millimeter, centimeter, something like that. So let's figure it out. Let's put the numbers in here. What we have for alpha for steel is 12 times 10 to the minus 6 per degree Celsius. Our initial length is 1 kilometer, or 1 times 10 to the 3 meters, times delta T. Now we're going from 0 to 38, so final minus initial, that's 38 degrees Celsius, 38.0 degrees Celsius. We multiply that out, and what we get is 0.456 meters, almost half a meter. So we're talking about a length that's on the order of this long. That's a pretty big expansion if that's got to fit into every kilometer of railroad track. Now, railroad tracks are made so that they minimize the amount of linear expansion, so you don't have to worry too much about that, but it is definitely something that needs to be considered, especially if you have ever driven over a bridge, a long metal bridge. If you've ever seen one of these things here when you drive over onto the bridge, these are expansion joints which help take care of any linear expansion due to the expansion or contraction of the bridge due to temperature changes. So these things are like little fingers that fit into each other, and so when the bridge expands they can move into each other, and when it contracts they can move apart, so they can take account that change in length without actually causing the bridge to bend or anything like that and deform itself. So these changes in lengths are actually taken into account when large metal construction projects are made. There's actually a nice beneficial use for these variations in length expansion using a bimetallic strip. Now, I remember seeing these in my old house, and you might recognize these if you have an old house with an old thermostat in them. Sometimes bimetallic strips are made into coils like this, and this is how an old thermostat was made. You'd have a bimetallic strip, and then on the bottom of the strip would be attached a little vial with some mercury in it. So a little lump of liquid mercury. Then at one end of the strip would be 2 electrodes, and at the other end of the strip, 2 other electrodes. Now, when the coil, say, warmed up, it would expand and move this way. This vial would tip, and the mercury would flow down to one end, connecting these 2 terminals, making an electrical connection, and electricity would be able to flow through those connections, and then those wires would be connected to an air conditioning unit. So when the coil heated up, it would move, the mercury would flow down, turn on the air conditioner, the house would cool down, this would rotate back, the mercury would move away, and the air conditioner would go off. And then in the summer, in the winter time, if this coil got too cold and contracted, the mercury would flow down to this end, would connect these 2. These were then connected to a heater. Your heater would turn on, warm up the house, the coil would rotate back, the mercury would flow off the terminals, and the heater would turn off. And so the thermostat was designed to maintain a somewhat regular temperature for the house, either turning on the air conditioner or turning it off, turning on the heater, turning it off, to try and maintain a regular temperature. And you could adjust that by rotating this coil one way or another to determine what temperature you wanted your house set. All right, so the basic idea is that when we add energy to an object, we're adding internal kinetic energy to its atoms and molecules, the temperature goes up. When we remove energy, the atoms and molecules have less internal energy, the temperature goes down. So the temperature of an object is essentially a measure of its internal kinetic energy, the internal kinetic energy of the atoms and molecules. Now, why is it that heat flows from one object to another? Well, we can think about it that way, that if we have a hot object and we put it in contact with a cold object, the atoms and molecules of the hot object are moving around much more. They bump into the atoms and molecules of the cold object, and so we've got warm atoms and molecules bumping into cold ones, giving them energy so that they start moving. These lose energy, these gain energy, and so the heat flows from the warm object into the cold object just from the connection, the touching between the atoms and molecules, you might say. So we can measure this temperature change for particular objects. Imagine we've got some material. We add heat to it. So we add energy. Heat is energy. We add the heat to it. Typically, the letter that we will use to represent heat or heat energy is a capital letter Q. So we add some heat to it. What do we expect? We expect the temperature to go up. So we expect to have some change in temperature. How much change in temperature do we expect? Well, the amount of temperature change we would expect to be proportional to the amount of heat that we put in. The more heat added, the more the temperature goes up. The larger this thing is, the less temperature change we would expect. If we added some energy to our object, to a small object, we would expect maybe a big temperature change. If we added the same amount of energy to a much, much larger object, we would expect a smaller temperature change. we can represent that in different ways, the number of atoms or number of molecules or something. The way we will do it is in terms of the mass. So the temperature change we expect to be inversely proportional to the mass. Well, we would also expect it to somehow be dependent on the material. So different materials would have different temperature changes for the same amount of energy. Well, we're going to write this whole thing as an equality, but rather than writing it in terms of delta T, we'll actually write it in terms of the heat. So let's bring all this over to the other side, and we'll write this as Q equals M delta T, and then the dependence on the material we will write as a lowercase c, where c is what we call the specific heat capacity. The specific heat capacity of the material, and different materials will have different values for the specific heat capacity. Now the units of C will be the units of Q. Q is a heat or an energy, so that will be joules, divided by the units of M, mass, so kilograms, divided by delta T, or a temperature, degrees Celsius. So the units of C, the specific heat, will be joules per kilogram degrees Celsius. Now sometimes heat in an object is measured by a different unit, a calorie. Now 1 calorie, 1 calorie is equal to 4.186 joules. 1 calorie is the amount of heat required to increase the temperature of 1 gram of water 1 degree centigrade. So that corresponds to a heat of 4.186 joules, and we'll actually do an experiment in lab determining this relationship. But typically we will be using energy in terms of joules. All right, so let's try an example. Let's stick some numbers in here.